Greetings. My name is Tom Fay, and on behalf of the Aircraft Engine Historical Society, I'd like to present a technical description of the Pratt & Whitney Allison 578DX Propfan demonstrator engine. Before we look at the 578DX, a little bit of Propfan history is in order. The Propfan is equivalent to an unducted fan, a UDF, or an ultra-high bypass engine, the UHB, or in more modern terminology, the open rotor. The American prop fans of the 1980s included the NASA ATP, which is a single rotation engine, the SR-7L, the GE36 gearless prop fan, and the Pratt & Whitney Allison 578DX. Subsequently, there were three other engines that at least have been run, and two of them flown: the Progress D236, the Progress D27 engine, and the Safran open rotor, but those are topics for another time. An earlier video in this series was done on the GE36, which was the first dual rotation prop fan to fly. That video can be found at the link shown and includes a history of the early prop fan programs. Flight testing occurred starting August 20th, 1986, and this engine flew at least through the fall of 1988. So what is a prop fan, and why the interest in this technology? A prop fan is defined as a multi-bladed propeller with thin, highly twisted, highly loaded swept blades, which offer improved fuel efficiency over propellers and turbofans. Why are the prop fans more fuel efficient? Thrust is a function of momentum, and for any given momentum, it is more efficient to move a large amount of air more slowly than a small amount of air much faster. The basis for this is that momentum is defined as mass times velocity. However, the energy required to generate momentum is 0.5 times mass times velocity squared. Thus, fuel efficiency is improved by reducing the velocity of the airflow for a given momentum. The yardstick for measuring the fuel efficiency of a jet engine is the thrust-specific fuel consumption, TSFC, which is defined as the amount of fuel used per pound of thrust per hour. The pure turbojet engine, as exemplified here by the J47 of 1948, all of the inlet air was processed through the jet engine to generate thrust, and it used 1.01 pounds of fuel per pound of thrust per hour. The turbofan engine, which had a bypass ratio of 1:3, as exemplified by the JT8D of 1980, flowed up to 3 times more air around the engine than went through the engine, and this resulted in a 27% improvement in TSFC over the pure turbojet engine. The high bypass turbofan, with a bypass ratio of 4:6, as exemplified by the CFM 56 of 1993, had a 59% improvement in TSFC over the pure turbojet engine. And finally, the ultra-high bypass turbofan, or prop fan, had a bypass ratio of 25:60, as exemplified by the GE36 of 1985. And this engine had a 63 to 76% improvement in thrust-specific fuel consumption, and thus the interest in prop fan technology. Simultaneously with the development of the single rotation prop fan, as shown in the lower right panel, NASA and industry became interested in the dual rotation prop fan, as it held the promise of a 6 to 8 percentage unit increase in efficiency compared to the single rotation design. This was due to the recovery of the swirl energy off of the 4-fan unit. It also provided increased total blade area, which reduced the loading on individual Propfan blades. Both General Electric and Pratt & Whitney Allison chose this design for their Propfan program. So what were some of the unknowns of the Propfan in the early 1980s? Full-scale articles are very expensive to produce and risky, so a huge effort was spent in computer modeling and wind tunnel simulations to guide the building of a full-scale article. The question remained, how good were these computer models at predicting how the full-scale article would perform? Could these models predict the acoustic behavior of the Propfan? Would the new generation of carbon fiber propeller blades of advanced shaping provide the sufficient strength, durability, and performance to advance the field? Could these rather heavy, highly loaded Propfans be safely and efficiently integrated into existing or near future airframes? Could systems be developed such as engines, gearboxes, pitch change mechanisms, cowlings, computer controls, mounting systems, etc., to support the promise of the Propfan? Last but not least was the public acceptance of the Propfan. All of these were significant challenges to the Propfan program. And now, on to the technical description of the Pratt & Whitney Allison 578DX ultra-high bypass demonstrator engine mounted on the custom port pylon of a McDonnell Douglas MD-80 flight test aircraft. The 578DX Propfan was built up from 3 major components and several sub-assemblies made by a variety of suppliers. The engine nacelle was made by Rohr Industries. The electronic engine control system was produced by Pratt & Whitney. The Allison 571 turboshaft power section was built by Allison, as was the gearbox, which took the output from the turboshaft engine and put it into the propulsor system. The engine isolator mounts were made by Berry Controls. Shown in this diagram in green is the low pressure compressor, LPC, low pressure turbine, LPT, and the Propfan drive. It is this low pressure system that provided the input power into the gearbox. The power section and the gearbox weighed about 2,700 pounds. The Propfan propulsor unit was designed, developed, and built by Hamilton Standard. It consisted of 2 discs, each with 6 blades. The blades were 52 inches long. The installed diameter of the propulsors was 11.6 feet. There was 26 inches between the centers of the propulsors, and they were designed to run at 1,235 RPM on both rotors. The blades were highly loaded at 70 horsepower per square foot, and the propulsor unit weighed about 3,250 pounds. This is the turboshaft power unit for the 578DX. The core engine is an Allison 571. The 571 was derived from a helicopter engine from the 70s, the XT701, which developed about 8,100 shaft horsepower. The engine was modified with the addition of a 3-stage low-pressure compressor with variable geometry stators. The engine had a 13-stage high-pressure compressor with 6 stages of variable geometry stators, and a 2-stage high-pressure turbine, which ran the compressor, and a 3-stage low-pressure turbine, which provided power to the output shaft to drive the propulsor unit. The engineering challenges for the 578DX Propfan project were significant. Could a gearbox able to handle up to 13,000 horsepower for up to 30,000 hours be developed? What about exhaust impingement on the Propfan blades with respect to noise, vibration, or thermal stress? How about vibration dampening and integration of the unit with the airframe? Blade off integrity of the engine and propulsor unit were also of concern. Propfan pitch control, the mechanics and control logic, speed of response, etc. were quite significant for the time. A further challenge was that the core engine for the demonstrator was somewhat underpowered. The key to the 578DX is the planetary reduction gear system. Shown here is a generic planetary reduction system, with the input gear being the center sun gear. The orbiting planet gears are carried by a planet carrier to be described momentarily, with an outer ring gear. The reduction ratio is determined by the relative sizes of the sun gear and the planetary gears. This brief video clip shows a planetary gearbox in action. Notice that the triangular planet gear carrier rotates in the opposite direction of the outer ring gear, and this is how counter-rotation is achieved in the 578 gearbox. Planetary gears are commonly used in electric screwdrivers as well as automatic automobile transmissions. This is a photograph of the actual sun gear and ring gear from the 578 reduction gearbox. Of note is the use of helical cut gear teeth. Helical cut gear teeth provide greater tooth contact area than straight cut spur gears for any given gear diameter. This photograph shows the planetary gear carrier of the 578DX gearbox, with the planet gears seated inside the planet gear carrier. The input receiver accepts power from the 571 turboshaft engine to drive the sun gear, which is not visible in this view. This is a photograph of the actual Allison differential planetary gearbox for the 578DX. Two of the planet gears can be seen in this view, and the sun gear is the central input to the gearbox. There is an uneven torque split between the fore and aft components due to the relative sizing of the sun and planet gears. In brown, the planet gear carrier drives the aft Propfan counterclockwise when viewed from the front at a nominal 1200 RPM, transmitting almost 5,800 horsepower at takeoff. In green, the outer ring gear drives the fore Propfan clockwise as viewed from the front at the nominal 1200 RPM, transmitting up to 4,500 horsepower at takeoff. This differential planetary gearbox design allowed for different rotor speeds for the fore and aft components, which was governed exclusively by blade pitch. This side view of the gearbox shows the input coming in from the left at 9,500 RPM, and at the right, on the outer part, is the flange that drives the fore Propfan. In the center is an output which drives the aft Propfan. The reduction ratio is 8.33 to 1. The unit weighs approximately 650 pounds and is 99.3% efficient. And lastly, a more technical schematic of the Allison gearbox for the 578DX is shown here. In yellow is the stationary gearbox housing. The bearings and roller elements are shown in orange. Coming from the left in red is the input from the turboshaft engine going to a sun gear present at the center of this drawing. The sun gear drives the blue planet gears. The blue planet gears are held by a brown planet carrier, which is the aft prop fan drive. The blue planet gears also drive the green ring gear, which drives the fore prop fan unit. Of special note, towards the top is the flexible mount for the green ring gear. This flexible mount was a key technology used to dampen the vibrations of the prop fan rotors from going back into the gearbox. In light green are shown accessory drives, some of which were driven off the main input shaft from the turboshaft engine, and others were driven off the planet gear carrier in brown. So how do you test and develop a gearbox for 13,000 horsepower? The most efficient way is the use of a nose-to-nose gearbox test rig. This rig allowed the testing of highly instrumented gearbox components under simulated flight loadings and power loadings in the laboratory. The 578DX gearbox underwent 556 hours of testing on this gearbox rig. Shown diagrammatically at the bottom is how this unit operates. Moving left to right, first component is a 1,000 horsepower electric motor, which is connected to a 5-to-1 speed increaser. Thus, the red shaft output is 10,000 RPM, much like the RPM output of the 578DX power section. That red shaft drives the green test gearbox, shown at the right. To apply a load to that green gearbox is a secondary gearbox shown in purple. And that purple gearbox is restrained by the blue torque applier. So varying amounts of torque or resistance can be applied through that blue device to get the desired torque loadings and power loadings to evaluate the gearbox. The differential planetary gearbox design of the 578DX allowed differential rotor speeds for the fore and aft prop fan rotor components. The relative rotor speeds were governed solely by the prop pitch, essentially the drag of the blades. This allowed the possibility of testing differential rotor disc speeds as a means to modify noise, vibration, or the efficiency characteristics of the prop fan unit. The independent disc speed control required extremely rapid and precise control of pitch on each of the propulsor discs, all scheduled by the modified Pratt & Whitney 2037 electronic engine control system. This controlled fuel flow, variable stator positions in the compressor bleed, and prop fan blade pitch in each of the two prop fan components. The limited flight time did not allow testing of differential rotor speeds in flight. This is a photograph of the Allison 571 power section on a test stand without the gearbox and the prop fan propulsor modules. Of note are the 9 angled lobe-style exhaust stacks coming from the turbine, and the gearbox would be located in the center of these exhaust stacks. Shown here is the propulsor unit of the 578DX mounted on the whirl rig. Instead of the prop fan blades, precisely designed weighted stubs are used, and these accurately replicate the centrifugal forces and twisting moments of the prop fan blades. The whirl rig allows for the testing of proper functioning, pitch control, and balance of the two rotor discs. This photograph shows the 578DX mounted on the modified pylon in an Allison test cell located in Indianapolis, Indiana. So what mechanism did Hamilton Standard use to change the pitch of the Propfan blades in the 578DX? Shown here is the aft Propfan hub with the pitch change actuator. This actuator assembly was located on the center line of the propulsor unit. The blue rotating ball screw jack can be thought of as a hollow threaded screw. The red actuator can be thought of as a nut. When the blue jack screw is rotated, the red actuator will translate fore aft on the ball screw. The green link rods connect the translating actuator to the eccentric pins on the base of the Propfan blades. The pitch lock screw is a very fine pitch screw that turns in synchrony with the ball screw jack and will lock the actuator in place if electrical power is lost to the pitch change motor. This is a cross-section view of the pitch change actuator assembly for the aft Propfan unit. In blue is the ball screw jack sitting on the center line of the propulsor. The red is the actuator unit, and the green is the link pin which joins the actuator to the eccentric pin on the base of the aft Propfan blade. So depicted here is the full Monty of the 578 pitch change mechanism. There are two sets of slip rings denoted by the letter A, two sets of electric motors designated by B, two sets of reducing gears designated C, two ball screw jacks D, and link pins E on the blade of each base socket. All of the components denoted in red spin in one direction, and all the components denoted in green spin in the opposite direction. The bearings for this whole unit are shown in yellow. The pitch change rate is about 6 degrees per second. If you remove the elegant 7-foot-long tail cone of the 578DX, the pitch change gear reduction train for the aft propulsor is shown here. The electrical wires coming from slip rings come in from the 1 o'clock position down to the electric motor shown in the circle. Those connections, electrical connections, are shown potted with the red epoxy. A small pinion from that electric motor engages the primary reduction gear shown at the 6 o'clock position. The large primary reduction gear engages a small pinion at the center of the secondary reduction gear. The large gear of the secondary reduction gear engages a small pinion at the center of the tertiary reduction gear. And the outer part of the tertiary reduction gear engages the ball screw jack. Everything shown here rotates at 1200 RPM. Moving on now to discuss the exhaust impingement issue onto the blades of the 578DX. Shown here in the lower right-hand photograph is the proximity of the lobed exhaust to the fore rotor of the Propfan. In the upper left-hand picture, you can see the beautiful area ruling of the spinner assembly and tail cone, which minimizes drag for the unit. The Propfan blades of the 578DX operated immediately downstream of the turboshaft engine exhaust. Thermal loading of the composite blades was by far the toughest issue faced by blade designer John Violette. Differential expansion between the full-length aluminum spar and the composite fiber shell caused by the 500-degree blade temperature caused the lamination of these components. This was remedied by the addition of a 0.1-inch layer of silicone-based insulation between the composite shell and the aluminum spar for the lower 20 inches of the blade that was bathed in the exhaust stream. The buzzing bee noise generated by the 9 lobed exhaust nozzles impinging upon the blades created cyclical changes in lift and noise. Potential remedies for this included the incorporation of an annular exhaust diffuser or to exit the core flow downstream of the prop fan blades. This image shows the 578DX prop fan core installed in a test cell wearing the early arrow type or fishtail exhaust ducts. The lobed exhausts were used on the flight engine. Also of note is the large oil tank shown roughly in the center of the picture. The prop fan blades were designed and built by Hamilton Standard, Windsor Locks, Connecticut. The blades were 4 feet 4 inches in length and the installed prop fan diameter was 11 feet 7.2 inches. The 4 blades weighed 22 pounds each and the aft blades weighed 26 pounds each. They were built with a full-length aluminum spar covered by a carbon shell with a foam core. A 2-piece nickel steel bonded leading edge was attached to each prop fan blade. The propulsor was designed to tolerate 1 blade off simultaneously in each prop fan disc. This remarkable design achievement was made possible by both the light weight of the individual blades and having 6 blades per rotor disc. The nominal 1,235 design RPM gives a blade tip speed of 750 feet per second with the aircraft at rest. In the engineering phase of the 578DX program, a number of issues had to be dealt with, including the shape of the exhaust stream from the core engine. An annular design would constantly bathe the roots of the prop fan blades in hot air, and thus a higher temperature actively cooled blade was considered for this situation. Cool air was funneled into a plenum in the leading edge, and the air channeled back underneath the skin to the trailing edge of the blade where it was discharged overboard. The geometry of the lobed exhaust system design allowed pulses of ambient air to hit the base of the blades between the pulses of hot exhaust air. This allowed the use of a passively cooled blade design in the demonstrator engines. Shown here is the insulating shield at the leading edge, which was carried underneath the skins to the back of the blade, and this allowed the temperatures to remain below the 500-degree Fahrenheit limit demanded by the aluminum spar, and proved very successful in the flight operations.
Prop fan blades, invented by Hamilton Standard during the mid-1970s. Their thin, swept spar and shell construction represents an evolution from successful turboprop designs. The design has undergone years of intensive analysis and testing.
The design, engineering, materials, and construction of the prop fan blades was a remarkable achievement. At takeoff on the 578DX, each blade produced about 1,700 pounds of thrust while absorbing nearly 900 horsepower. The prop fan rotors could be synchrophased, which means the timing could be adjusted for where the blades cross each other to minimize noise or vibration. Both prop fan rotors could be feathered and reversed. And in fact, the MD-80 demonstrator aircraft was backed up by using reverse on the 578DX alone. Like any novel, complex electro-aeromechanical system, the 578DX had its fair share of developmental issues. The original pitch change control system, so-called BAC or beta actuator control, was erratic. This required a complete redesign of the system, ultimately by GM's Delco Remy division, and this caused a significant one-year delay to the program. The Propfan blade pitch change motors were sealed but surrounded in up to 250 degree Fahrenheit oil, and the whole assembly rotated with the Propfan propulsor at 1,235 RPM. Oil intrusion frequently resulted in short circuits in these motors. Allison engineer Francis Kahn and again the GM Delco Remy division remedied the problems but caused a 3-month delay to the program. Early in the program, Propfan blade stress limits were set so low by Hamilton standard that ground testing, let alone flight, could not be undertaken. Finally, Allison calculated their own limits and proceeded with ground testing followed by flight test. This caused a 3-month delay. The 578 installation on the MD-80 demonstrator had marginal performance in meeting the OEI one engine inoperative standard at takeoff if the JT8D turbojet engine failed. So a water alcohol injection system with a 500-gallon fuselage tank was installed. The system flowed 16 gallons per minute into the engine, boosting the 571 core engine power by about 15% to somewhere around 10,400 horsepower. The water system required a significant engine and airframe engineering effort, and it was used for all takeoffs. The 578DX utilized 2 aft elastomeric engine mounts to handle the vertical, lateral, and thrust loads of the engine. These mounts exceeded 250 degrees and showed delamination during extended ground running, necessitating the ducting of air-conditioned cabin air to cool the mounts. The forward mount, which handled vertical and lateral loads, was a metal mesh type isolator that was not heat limited. Throughout the program, oil cooling was marginal for the propeller lubrication system, hovering near or exceeding the 167 degree Fahrenheit limit. Engine and gearbox oil temperatures ran just below the max limits. The oil cooler was likely undersized or suboptimally ducted. The flight crew for both the GE36 Propfan program and the 578DX program was from McDonnell Douglas. And the flight crew had stringent requirements for a full crew whenever the engine was run on the ground, and that only 1 flight test be done per day, all of which resulted in a 3 to 4 months of extra time. Many in the Pratt Whitney Allison program believed there was a flight crew bias against gearboxes and flew or did not fly accordingly. The self-locking fasteners on the nacelles, which were made by Rohr, were opened and closed so often that they were wearing out. The aircraft could fly with a maximum of 20% of the fasteners compromised, and the fasteners were quite difficult and expensive to replace. There were over 800 individual monitored parameters for the engine, nacelle, propeller, blade, gearbox, airframe, pressure, temperature, stress, all recorded by the Pratt & Whitney, Allison, and Douglas data systems. Keeping all these sensors calibrated and in operational condition was truly a challenge. The flight program for the 578DX was designed for 50 flights. However, only 14 flights were made for 20 hours of total flight time. This was accomplished over 5 weeks when lack of funds terminated flying.
The initial 578DX Propfan propulsion system has completed assembly and installation on the test stand at Allison and is currently undergoing testing. Let's join John Spratt and other Pratt & Whitney, Allison, and Hamilton Standard team members as they complete the initial test.
Hi. Starter air is on. High rotor speed, 1850. 2500. Ignition and fuel are on. We're fired. High rotors 5,000, 6,000, 7,000, 1,100, 1,300, 1,500 low rotor, 2,000 low rotor. MGT of 880 degrees, high rotor speed 10,500, low rotors 4,350, stable fire up, look good all the way. Prop speeds are 427 forward and 610 aft. Oil pressures at this point are engine 89, gearbox 68, prop 81. Vibration levels 0.3 on turbine lateral is the highest. Everything else is below 0.15. We're stabilized high rotor 10,489. Low rotor is 4,500. Prop speeds 438 forward, 624 aft. MGT is 890. Oil pressures 81 engine, 57 gearbox, 63 on the prop. Vibration levels are 0.31 on turbine lateral. Everything else below 2/10. Fuel's off.
Flight testing. Combinations of tip speed and differential rotor speed are among the variables tested. Progress is made toward achieving cabin noise and vibration goals.
Despite the truncated flight program, the 578DX demonstrator achieved a great many things. Flight performance out to Mach 0.77 at altitudes up to 30,000 feet was achieved. Gearbox performance was deemed excellent, with engine and gearbox vibration levels acceptable in all flight regimes. Stable power transitions and smooth operation of the power system allowed for unrestricted operational testing. Blade stresses remained at or below 70% of the maximum allowed for all flight conditions, including takeoff, climb, cruise, descent, landing, and reverse at up to 100 knots ground speed, all of which allowed for unrestricted operational testing. Prop fan blade temperatures remained within acceptable and predicted range in all stages of flight. One of the great unknowns of the whole prop fan program was noise generated by these engines. Only 3 flights of the 578DX could be made for calibrated testing of the noise that occurred during takeoff, flyover at 2,000 feet, and route noise at 30,000 feet at cruise, and near field, meaning inside the cabin, noise acoustics. As a result of the limited flight time, variable atmospheric conditions during these flights, and equipment malfunctions, data quantity and quality was insufficient to correlate the collected data with the computed predictions. The 578DX made 10,400 horsepower by torque meter on the Allison test stand. However, once the system was installed on the MD-80, even with the addition of methanol water injection, only 9,782 horsepower could be achieved. Thus, performance and acoustic testing at high power settings were hindered by insufficient dry power, which was about 8,500 horsepower. This installed power shortfall was unexpected, unsolved during the flight test period, and concerning with respect to future growth potential of the 578DX. The maiden flight of the 578DX installed on the MD-80 occurred on April 13, 1989, and some 5 weeks later, the last of the 14 flights occurred on May 20, 1989. In the words of Al Novick, Director of Large Engine Business Development at Allison, the operation was successful, but the patient died. 1989 marked the end of the American prop fan projects. Crude oil prices had dropped to sustainable levels. Government, military, and corporate funding had ceased for the prop fan projects, and significant engineering challenges remained. These included noise, safety, airframe integration, reliability, installed weight, cost, engine maker, airframe maker, airline, and public acceptance. In other words, who's going to be the first to buy into this technology? The termination of the prop fan programs does not diminish the groundbreaking achievements made by the prop fan demonstration teams. Shown here are the 55 men and women of the 578DX flight support team. The highly prestigious Collier Trophy is awarded for the greatest achievement in aeronautics or astronautics in America for accomplishments demonstrated by actual use during the preceding year. The NASA, GE, Pratt & Whitney, Allison prop fan project was awarded the Collier Trophy for the year of 1987. Both of the 578DX engines survive to this day. The 578DX unflown development engine is held by Pratt & Whitney in East Hartford, Connecticut in the USA. The 578DX flight engine is held in the collection of the Rolls-Royce Heritage Trust Allison Branch Museum located in Indianapolis, Indiana in the USA. Of note is an example of the gearbox shown within the red circle. This table shows comparative data for the two American Propfan demonstrator engines flown in the late 1980s. While both of these units have the same Propfan diameter of approximately 140 inches, the installed lengths, nacelle diameters, and weights are significantly different. The thrust-specific fuel consumption of 0.24 to 0.315 are at least 25% better than the 0.42 SFC of the modern CFM56 turbofan, as indicated in the box at the lower left of this graphic. Also of note is the weight of the Propfan demonstrators, which are considerably heavier than that of the CFM56. As a reference to the Propeller era, the activity factor of 150 to 180 for the Propfan blades is much higher than the 105 of a World War II era propeller. The activity factor is basically an index of the ability of a blade to accept horsepower. Also of note is the blade loading. The Propfan blades are loaded at approximately 85 to 70 horsepower per square foot of disc area, while the World War II era propeller is loaded at about 25 horsepower per square foot. Despite the reality that Propfans were never commercially produced, the American Propfan programs were in no way a failure. Rather, they pioneered the materials, systems, and technologies essential to every modern turbofan engine. The efficiency design goals were actually met. Advanced gearboxes were developed, as were thin, lightweight composite fan blades, and the validation and adjustment of computer modeling of noise, fluid dynamics, vibration, and structures that has enabled the cost-efficient design of novel technologies all had their beginnings with the Propfan project. I'd like to acknowledge and express my great appreciation to the 10 people cited at the top of this page for their help in documenting the 578DX program, as well as the wonderful resources of the Rolls-Royce Heritage Trust Allison Branch Archives located in Indianapolis, Indiana. And with that, I thank you for your attention.